Let's finish up our study of Chapter 36, Geometric Optics, with some applications of these optics. In particular, let's look first at a combination of thin lenses. Here we have a linear setup of two lenses. And we'll approach this problem as two individual problems. We'll look at the first lens, deal with that problem there, the object and the image. And then once we get where the image is and what kind of image it is, we'll forget about the first lens and deal with the new problem of the image being the object for the second lens. And we'll deal with the second lens on its own. And then our final result will be the image of that second lens. So the image of the first lens is calculated as if the second lens were not present. And then the light will approach the second lens as if it were the object is the image of the first lens. So the image of the first lens is treated as the object of the second lens, and then we get our final image of the system from the second lens. That's our approach. So it's really, just a straightforward approach, dealing with two lenses separately and then superimposing the result together. So here's an example. We're looking at the first lens. We have our object, and a ray coming in parallel is going to be focused on the focal point of that lens and proceed on from that point. A ray going through the middle of this lens will go undeterred, and those two rays will form the tip of that image, and so we can locate the image there. We could add a third ray if we want. One going through the focal point will come out parallel, and again that helps us form where the image is. So we know where the image of the first lens is. We'll bring in the second lens, and now the image of the first lens becomes the object for the second lens. And we can forget about everything else that preceded that, at least in our analysis. So we'll get rid of the first lens setup, and now we have a new problem where we have a new object and a new lens, and we'll deal with that problem. This object happens to be inside the focal length of the second lens, so we're going to have it diverge, and we'll have to draw backwards in order to get where our final image is. Right there. So that will be our final image of the second lens, and hence the final image of this double lens arrangement. Note that if it had been possible that the image of the first lens had gone beyond the position of where the second lens would be, hence on the back side of the second lens, the first lens image would then be treated as a virtual object for the second lens, because there wouldn't actually be, the object for the second lens wouldn't actually be comprised of real rays. The object actually would originate on the opposite side of the incoming rays, and hence the object distance will be negative in that particular case. So if this image I1 were over to the right of this lens 2, our object distance would be negative because it's not on the side of the actual incoming rays to that lens. And then we treat the problem with the same mathematics from there on. If we have a magnification of this kind of setup with two thin lenses at large distance like this, our overall magnification would be equal to the product of the two magnifications of each lens. So you have the first lens, negative Q over P, times the magnification of the second lens, negative Q prime over P prime, and that magnification would be our overall magnification of the two lens system. In dealing with these optics, we have to deal with the possibility of spherical aberration. Because of the shape and size of the lens, light that comes in towards the top and bottom are going to be refracted slightly different than, say, light that comes in closer to the middle where the lens is closer to being flat. So they're going to converge at different spots, and you're going to get some blurriness in your image where they converge. We call that spherical aberration, where light rays far from the principal axis have different focal points, and they converge at different points on the principal axis, or near the principal axis. So a little bit fuzziness. One way to correct that maybe is to change the shape of your lens a little bit. Maybe not use a spherical lens as much as a parabolic lens or something like that. Chromatic aberration is a possibility as well. Different wavelengths of light refract by lens at different points. We saw that there's dispersion for different wavelengths of light, different refraction, and they would converge then at different points. So violet might converge at a different point as opposed to red, thereby giving us again some blurriness due to the color refracting differently. A combination of converging and diverging lenses can possibly minimize a chromatic aberration effect just by mitigating these effects in opposite directions. The camera. Here's an old style camera where you have a lens, aperture, object distance, image distance, a film to form the image. To get a sharp imaging depends on your lens to film distance, which in turn depends on the object distance and the focal length of the lens. Depends on the shutter, selecting the exposure time. More exposure time will give you more light. The aperture, having an adjustable diameter, adjusting more size to the aperture will also give you more light. Maybe you don't want more light. Maybe you want more resolution to your image or more definition to your image. So that's something you have to adjust. Spherical aberration can be minimized by using a small aperture. There's another reason to use a small aperture. That way you don't get the fringe effects of the edges of your lens. So use a small aperture to get the middle part of the lens. Might need a larger exposure time if you do that, so you can get minimize aberration, get a nice clear image. The intensity of a camera, the intensity of your setup, is proportional to the diameter of your aperture squared, which indeed is being proportional to the area allowing the light coming in, and inversely proportional to your focal length squared, as the distance to the film squared. So we have what we call an F number, which is equal to your focal length divided by the diameter of your lens. And your intensity will be inversely proportional to this number. As your F number gets larger, the amount of darkness in your image will get larger as well. In other words, a low F number will have a brighter image. Higher F number will be a darker image. We often give this as the speed of the lens. A lens with a low F number is a fast lens. If you have a low F number, you have a larger aperture, get a lot of light, create your image in fast time. And if you have a larger F number, less light, you're going to have to give yourself more time to give yourself an image, so you're going to have to change your exposure time. If you were to double your F number, you would have to increase your exposure time by doubling squared, by 4 times. So every time you double your F number, increase your exposure time by 4 times to get basically the same image. Here's a simple magnifier, and in this particular case, what you're really doing is increasing the angle that is being subtended by your image, and hence making it look bigger. So here's our object. Light comes in here, it's diverging on the way to your eye, and hence it appears to have a greater angular extent than it actually does. Based on this, we can really think of magnification for these kinds of optics in terms of how much the angle to your eye changes. Normally you have your eye, near point of the eye is located 25 centimeters away from your eye. That gives you a certain angle extent to an object. Let's call it theta naught. And if you put a lens in front of that, that will increase the angular extent that gets to your eye. And we can define the magnification of that lens in terms of a ratio of these angular extents. The magnification will be equal to the new angle based on the lens as opposed to the angle that would be based on the near point of your eye at 25 centimeters away. So that's magnification, angular magnification, theta over theta naught. Here's a compound microscope. We have two lenses. It gives greater magnification than a single lens. The objective lens has a short focal length on the order of, say, 1 centimeter. And the eyepiece lens also has a relatively short focal length, maybe a few centimeters. So the length between these lenses is much greater than either focal length. But what we can see in this particular setup, that we have the image of the first lens coming to the eyepiece and then diverging over a small portion of this eyepiece, creating a very, very large image of the object. And hence we can get a magnification of that object. Telescopes. Say you want to look out in the universe and look at objects in the sky, and one of the more famous objects would be Saturn and Saturn's rings. In 1774, English astronomer William Herschel mounted several 9-inch mirrors in a 10-foot-long telescope and recorded with satisfaction that he had spent the first night looking at Saturn's rings and two belts in great perfection. And you can tell that since he saw the two main belts, that he indeed was looking at Saturn with very good resolution. There's two fundamental types of telescopes. A refracting telescope uses a combination of lenses to form an image. Those are the first kinds of telescopes, the kind of telescope used by Galileo. And a reflecting telescope uses a curved mirror and a lens to form an image. That's the design first proposed by Newton. Telescopes can be analyzed by considering them to be two optical elements in a row. The image of the first element becomes the object of the second element. For a refracting telescope, it would be two lenses. For a reflecting telescope, it would be a mirror and then a eyepiece lens. Here's a refracting telescope. Two lenses are arranged so that the objective forms a real inverted image of a distant object. The image is near the focal point of the eyepiece. So you have your objective lens with a focal length, and its focal length or focal point is very close to the focal point of the eyepiece itself, so that the length between the two lenses is actually equal to the sum of the focal lengths of the two lenses. The focal length of the objective and then the focal length of the eyepiece. Ultimately, the eyepiece will form an enlarged, inverted image of the first image. So you have the image very near the focal point of the eyepiece, and that allows you to get a very large image of the object. You can put that into the thin lens equation and verify that for yourself. Refracting telescope disadvantages. Large diameters are needed to study distant objects. And because you have large diameters, they're difficult and expensive to manufacture, to create a large lens like that. And the weight of a large lens leads to sagging, which produces aberrations. So the glass is actually amorphous, and it's actually a real slow-moving liquid. And so if you had a large lens under gravity, eventually the glass would move and create aberrations to your image. So the reflecting telescope devised by Newton is actually better. It replaces the objective lens with a mirror, so you don't have to worry about the aberrations due to the objective lens. The mirror is often parabolic to overcome spherical aberrations. In addition, the light never passes through the glass, so you don't have chromatic aberrations. And you only have to worry about the eyepiece. So chromatic aberrations are reduced to just what is given to you by the eyepiece lens itself. Also, the mirror can be much better supported against gravity, and there's no sagging due to gravity because the mirror is just a surface. Here's a look at the Newtonian reflecting telescope. Incoming rays are reflected off this parabolic mirror, come towards this smaller mirror at point M, in which they are focused onto an eyepiece toward point A. You could actually put a photographic plate here at M and then avoid the chromatic aberration of the eyepiece, and so you wouldn't have to look at it. You just have the film right there. Examples of telescopes. The largest reflecting telescopes, and most of the telescopes used to study the sky are indeed reflecting telescopes because they, as we just said, they have a multitude of advantages over refracting telescopes. The largest in the world are the 10-meter diameter Keck telescopes on Mauna Kea in Hawaii. And Mauna Loa. Largest single mirror in the United States, the continental United States, is a 5-meter diameter on Mount Palomar in California. The largest refracting telescope in the world is the Yerkes Observatory in Wisconsin, which only has a 1-meter diameter, which is pretty large anyway for a refracting telescope, but compared to these reflecting telescopes, has a much smaller area. Here's a picture of the Keck telescopes in Hawaii on Mauna Kea. If we were to look inside, we can see the diagram of the construction of the reflecting mirrors, focusing on a point just above the mirrors where you could either have a lens or some kind of light collecting device. Here's the Yerkes Telescope. Looks like it's set up to look at something, so let's go ahead and look inside this telescope. We're going to look inside the eyepiece, and what are we looking at? Oh yeah, it's focused in on, you recognize the object? Mars. Right in front of you is the big crack across Mars called the Valles Marineris. Likely it happened because on the opposite side of Mars is a huge basin, the Hellas Basin. So something could have hit Mars in ancient times and caused it to kind of bulge on the opposite side where it cracked. And we see the Valles Marineris as a result of that. Now let's look even further. Let's say if we looked at the surface of Mars, we might see some interesting features on the surface. This is actually a picture taken of the surface of Mars when they were looking for a place to land the Viking landers back in 1977. And NASA released these photos, and they look pretty interesting. Looks like this could even be a picture of a hippopotamus over here on the side, and maybe Gumby right here upside down. And then there's a picture here. That's very curious. Some people thought that kind of looked like a face. No? people want to see things that are familiar in pictures, and so maybe part of the problem is you might be seeing something that you wish to see, which would be a face. The other possibility is, on Mars, there is some water. There's water all over Mars. It's about, just below the surface. And it's icy water because it's very cold there. So there's a lot of water. There's a lot of ice. Maybe one of the most popular things to do on Mars is to play hockey. And maybe this is a monument in honor of Hall of Fame goaltender Grant Fuhr. It looks a lot like Grant Fuhr. So maybe they, just honoring the sport of hockey with this monument to goaltender. Actually, here's a picture of the face taken by the Viking in 1976, and kind of looks like a face. But here's the same picture taken by the Mars Global Surveyor in 2001 with a little bit higher resolution, and we can see, maybe not really a face. Unless you're a fan of the Phantom of the Opera, it's not really, doesn't really look like anything intelligent in that face. All right, it might be an ode to some kind of intelligence to some point, but that's a matter of opinion. All right, so we're going to conclude this lecture and leave Mars and other telescopic devices, and we will progress onto other features of light in the next chapter.